All right, good morning, everybody. So, you have watched, I hope, the video on rates of change. And okay, so let's just quickly review that before diving into the heart of calculus, really. Very important lectures coming up. I cannot stress the importance of the next lectures enough. Okay, so let's remember. Instantaneous, I have to sound it out, rate of change of, let's say, my function at some x value, let's call it c, is the limit as not x, h approaches 0 of f of c plus h minus f of c over h. Do we call it an a? Who cares? This, it's helpful to understand, for sure, where this limit comes from. It definitely helps me to remember it, but it's not crucial. At the end of the day, you have to remember what is in this box. There is no way around it. There are variations of this limit, but I don't really see the point in worrying about that when this guy is all we're going to need. Now, where this came from very roughly is we have the graph of our function. Let's draw it like that. This is y equals f of x. And let's suppose our point here is c. We're interested in what happens exactly at x equal to c. Not in a window averaging out all the information over that window. We want to let the window size h shrink down to 0 essentially, but we can't actually have a slope secant line with no change in the x value, because then we're dividing by 0. So that's not going to work. Hence, we look at the behavior and see which way are these secant lines headed. So secant line has a slope, change in y would change in x, slope, slope as we let this window change. What we end up with then is the slope of the tangent line at x equal to c. So this limit definition graphically is interpreted as the slope of the tangent line at the x value in question. Very important. So when we talk about a function, like a distance function changing over time, sure, the rates of change are the speed or velocity values. If we look at it graphically, what we're talking about when we talk about the rate of change is the slope of tangent lines. And it comes from the argument, where the same argument that gave us this limit leads us to the tangent line conclusion. Okay, so I'll put this in a box as well. Just a graphical interpretation of instantaneous rate of change. Whoopsie, what did I just do? That's not a page I want. Graphical interpretation, rate of change, instantaneous rate of change, limit definition, slope of the tangent line. These are all the same thing. Okay, all the same thing. Now, people weren't happy with the long word instantaneous rate of change of a function. They wanted to give it a new name, a shorter, more catchy name, I guess. Yeah, my tangent line got a little away from me there. I totally admit there. Let me clean this up for you. Kind of, to be honest, if you have to ask which line is the tangent line, then I'm not sure you watched the video yesterday, because we drew these secant lines. Line connecting 2 points on the graph is a secant line, and the slope of that line is the average rate of change. As my window h is the window size, as it gets smaller, the second x value drifts closer to c, then the secant lines approach what we'll call the tangent line. Right? It's all in yesterday's video. So we are going to give this a new name, and that name is going to be the derivative of the function. So now we have a whole bunch of things that are sort of interchangeable. They all mean the same thing, just depending on the setting. I have instantaneous rate of change. I have the limit definition, the limit version. I have the graphical view, the slope of the tangent line at that point. I have the short, more popular name, the derivative of the function at that x value. All of these things in the boxes mean the same thing, exactly the same thing. And depending on your setting, depending on the question, you can jump between these as you wish. They all mean the same thing. Okay. Very important. It's all the same thing. It's all the same thing. Actually, I did not want to open that page. It's not the page I want. Could you stop jumping pages? I want to make a page that is this size, letter size. Okay. So let's do a problem in chapter 4. I'm going to jump right to the end, 412. That is the most important problem set in chapter 4. Chapter 4 is not, I'll call it chapter. In the problem book, topic 4 is sort of a crossover linking instantaneous rate of change to this derivative. So there's not much there. I want to do number 3, mainly because there's a typo, and now I do have to open the problem book, I think. So give me 1 second. There we go. Okay. And there we go. Chapter 4 is down here somewhere. There we go. Nope. Nope. There we go. Now there's a typo that the 2 is a little low. It's actually x squared minus 7, which is why I wanted to do this one so you don't get confused by this typo. So x squared minus 7, and the x value in question is 0. So my function here, x squared minus 7, oof, that's an ugly 7, and x is equal to 0. That is my point that I'm interested in. All right. Okay, so I can ask many questions here, right? They ask, use the limit definition of the derivative. I now know what that is. It's this box, the limit box. And they want to determine the derivative function at the point that I'm interested in. We'll do the second bit in a second. So I'm going to set it up, limit h goes to 0, f of 0 plus h minus f of 0 over h. I have to memorize that. There's no way around it. You memorize it. I'd like to give this a name, this derivative. Maybe I want to link the function, instead of saying instantaneous rate of change of the function. Well, the function in question is important. So maybe I want to write a short version referring to the name of the function. If the function was called f, I don't want to say the derivative of f. I want to maybe say I want to recycle the name of the function, but I'm going to put a little apostrophe there. And that is going to be the symbol for the derivative of f, the instantaneous rate of change of f, this limit definition, but it's at a specific x value, right? So I'm going to have to put the x value in question in there as well, so that I can capture all of this information in one go. Okay, so I have this, which we call a little prime symbol, when we say f prime, or just say derivative of f at c. So I can use that and say, well, in this case, I want the derivative of f at 0. All right, so just another name. Let's put it in the box. Another name. All of these things are the same. Different names for the exact same thing. Now I have to look at this limit. Well, I'm going to divide by 0. So let me first see what happens when I plug in the function here. So I have 0 plus h, so that's just the same as h. So f of h is h squared minus 7. And f of 0, so let's put round brackets around it. That's my first function evaluation. Second function evaluation is at 0. So that's a little bit easier. I plug in 0 for x, I get negative 7. I put that over h, and I'm still busy cleaning this up before I can really see what's happening here. I get an h squared minus 7 plus 7, so h squared over h. I'm just actually going to do it in one line because they're so short now. Save some space so I can see the whole thing. Then I can cancel some h's, and 2 h's at the top, 1 h at the bottom, so I have an h left. And h is a polynomial in h, so when h goes to 0, this whole thing is 0. So now I can say many things here. The derivative at 0 is 0. The instantaneous rate of change of the function when x is equal to 0 is 0. All kinds of things. And if I think about the graphical interpretation, I can say the slope of the tangent line at that x value is 0. Well, does that make sense? Let's look at this graphically. Because I took an easy function that is a single transformation of a basic function I have in my library, I can graphically easily visualize this. Let's do it like so. That's just the parabola shifted down. It's sort of okay. At negative 7. That's when x is 0. So I'm looking at the point right there. Well, that turning point, it now says the slope of the tangent line is 0, which means that the tangent line there is horizontal. Horizontal tangent line, which I hope feels right. It's the turning point. As I track the angle of this graph, so to speak, right at that turning point, it's going to be flat before it turns back up. So all of these things are saying the same thing. Derivative being 0, slope of the tangent line, it's all the same thing. It's all the same thing. Okay. So if I have a function and I want to find the slope of the tangent line, which we've answered here, we'll do the equation. Oh, we can do the equation. It's done. It's easy. The equation of this horizontal line, oops, equation is then simply y equals 7, right? 0 for m in my mx plus b form. If I have a function and I'm asking any of these questions, what is the derivative? What is the slope of the tangent line? What is the instantaneous rate of change? All of these things, it really goes through this limit definition. And after I've evaluated this limit, I can then interpret what this means graphically, what this means if it's a specific distance function or whatever. the issue may be. But they all go through this limit definition at some stage, really. Okay. All right. So I'm not going to be too concerned right now with the practical side of things. I want to figure out this derivative and better understand it, maybe first, to see how does this work. Yes, always keeping in mind that it's the slope, and we can make a side note here for sure. Maybe I'll do it over here. But for now, it's really a side note that if I have a distance function, let's say if we have a distance function, let's call it d of x, not x, distance over time, right? Time, distance function. Then the derivative, which will be d prime, well, this is the rate, so instantaneous rate of change, and the instantaneous rate of change is velocity, with the size being the speed and so on. So this represents the velocity function. So distance and velocity, or position, I guess is more accurate, and velocity is related through this derivative, through this rate of change. And let's call this, let's call it v for velocity. If I look at the derivative of, the derivative of velocity, which means v prime, then that is the instantaneous rate of change, Instantaneous rate or rate of change of velocity is acceleration. So they are related by way of this derivative again. We can call it a of a function or whatever. And then there are some problems in the book about velocity and position or distance and acceleration and so on. So there is, I guess, a little bit more practical side to derivatives that is not too bad to handle for us right now. But I don't really care too much until I better understand even how to find this derivative. So personally, I feel that I have to let the practical application side just rest a little bit until I'm ready to see those kinds of problems. I don't want to put a practical layer on top of a problem until I understand how does this limit work. I need to see more functions. I need to better understand this calculation of the derivative. Sure, keeping in mind the slope of the tangent line, rate of change, but it's this calculation. I don't feel I've seen enough to really understand how the function is related to this derivative. How are these linked? What is this limit definition telling me? So I have to look at that and take my time to better understand and get a sense for the relationship between the function and the derivative. And people glance over this way too quickly. And then they look back and they don't really understand what the derivative is and what it's really saying and how to find it. And what's the link between different functions, because they didn't take the time here to better understand how that limit definition leads me to maybe shortcuts and conclusions. Better understand the derivative. Whoopsie. Derivative. That's our goal now. Well, a good first attempt is to let's make the function just super simple and familiar. Let's take f of x as my square function, my quadratic function, my basic quadratic function. And now ask, okay, well, if I want to find, let's look at this function. There it is, parabola, super easy. I can draw it. Well, I try to draw it. It's not bad, it's not bad. Okay. Whether I shift it down by 7 or not doesn't have much impact on the slope values, right? So I already have some information that at this vertex, my slope is 0. Slope 0. Maybe I want to know what is the slope of the tangent line at 1. Okay, well then I'm going to have to find the derivative at 1. And I'll set up the limit definition, which I have memorized, f of 1 plus h minus f of 1 over h, and I have to find it. I'm going to leave you to it. You go through the motions, you do the whole song and dance. It takes a couple of minutes, if not more. You get a 2. So the slope is 2. Maybe I want to know what is the slope here at -2. So then I have to find the derivative at the value -2. I set up my limit definition. -2 plus h inside the first function, -2 inside the second function, over h. I go through the motions. A few moments later, I get -4, which makes total sense. It's negative. It's a little steeper, -4. But now I start to think, whoa. Even for this basic function, there are so many x values. How do I know which one you are interested in? Maybe you're interested in what happens at x equal to 0. Maybe x equal to 1. Maybe -2. But there's a ton of them in between. I don't know which one you want. For every new x value, I have to go through this song and dance of the limit definition every time. That does not seem very efficient at all. Why don't we just say, leave the x value open? Let's call it c. So leave, let's say leave the x value as, let's say, x equal to c. Don't pick a specific number. And then ask, what is the derivative at c? Sort of trying to come up with a formula, if you will, that if you want x to equal, if you want the x value to be 0, I'll plug it in. If you want it to be 1, if you want it to be -2, if you want it to be anything. Now I'm a little bit more flexible, but I have to figure out what this limit evaluates to before I can come up with my formula. It's a little bit more complicated because I don't have a specific number. Things won't simplify as nicely. Let's see what we get though, how far I can simplify this. Remember, I just have my quadratic function x squared. So f of c plus h is c plus h squared. F of c is c squared over h. I need to simplify this. C squared plus 2ch plus h squared, and c squared is still there, all over h. Now I see the 2c squareds cancel, and I'm going to have 2ch plus h squared over h. Now, okay, that's maybe as far as I want to simplify. Now I see, oh, well, the form of this limit is still 0 over 0, which means I need to try and simplify this more. I can do that by factoring out an h at the top, get 2c plus h over h. The h's cancel. I then have the limit being the same as the limit of 2c plus h. Now, the h is the variable in this limit. H goes to 0. The c is as if it's a specific number. So h is the variable thing. This is a polynomial in h. Plug in h 0 for h, I get 2c. So all of this to get a formula in this case, 2c. So that is now if my function is x squared, then the derivative at an x value that I've left open and called it c is given by the formula 2 times c. So that then means that if I want to know what happens at 0, I use this box. I don't use the limit definition. I've done the work once, and now I use the formula. 2 times 0 is 0. If I want to know what happens at 1, 2 times 1 is 2. If I know what happens at negative 2, 2 times negative 2 is negative 4. So now I'm in a much better position. I can find the slope values. Remember, these are derivative is slope of tangent line. I can find these slope values much more effectively. Without having to do the limit every single time, I now have a formula to handle any x value you may be interested in. Maybe these three, maybe some others. I am not going to have any problems now. I did the limit definition once, and now I can move on and not get stuck in that time-consuming side, because I understand better that for this quadratic function, only this one, the derivative is linked in some way. I figured out by way of the limit definition. So what I really have here is a new function. I have, if I put in the input, which we call c, I calculate the derivative as 2 times c, and I get my output, which is 2 times c. This is a function again. This is the derivative function. It still works with an input-output system. It's a function. The c doesn't actually matter. I can use x again. Wherever there's a c, I'll put an x. It's an x value. Why not write x? If my input is x, then I multiply 2 times that x value, and I'm going to get my output, which is the derivative of the function. So I have my original function, f of x equals x squared, and I have my derivative function, f prime of x equals 2x. Each one individually is a function. It has an input, it has an output. It's just calculating the output in a different way, but they're each a function. And the function aspect of the derivative allows me, if I can find this function, like I did up here, it allows me to get around the limit definition, the limit calculation that technically you have to do every time. But if I do it in an open, non-specific way, I can find the formula for the derivative, which I can see as a function, input, output. But at some point for a function, I do have to do this limit definition. I just like to minimize my work, so I have to do it once at least to find the function eventually. So that's one very important thing, that the derivative itself is a function related to the original function. That, of course, if I change the original function, I'm going to get a different derivative function. They are linked. The slope values very much depend on what the original graph is. As soon as I change the graph, the slope values are going to be different. As soon as I change the function, the derivative will be different. Function, original graph. Derivative, slope values. Okay. So we have a couple of things happening here. One, always, the original function has this derivative function connected to it. The question then becomes, if I change the function, how is the derivative function related to it? Can I see a pattern beyond using the limit definition? Okay, well, to do that, let's stick to our basic functions. And after I've now investigated and figured out x squared, what is my next basic function? Probably x cubed. That's the next polynomial that I have in my library. So let's have a look at it. Let's make a new page here. And of course, with a more complicated function, I'm going to get a more complicated derivative. That is reasonable. Now again, my goal here, of course I can see the graph, right? I know the graph. It's one of my basic functions. You should all know the graph immediately. Whether I can graph it neatly is another issue, but it's a little wobbly there. There we go. There it is. Different graph. So I'm still asking for slope values. What are these slope values? As I pick different x values to be interested in. Sure, I can go and pick a specific x value, plug in the limit definition, and say, for example, let's say I want to know the slope at x equal to 1. Well, that is the derivative at 1. I set up my limit definition, f of 1 plus h minus f of 1 over h equals. But I know that even if I did this, which might not be a small amount of work, what if you want another x value? What do I do then? I'm gonna have to do this again? No. Let's just stop this before it even starts. By just keeping the x value open. Let's maybe call it a c, if it helps you. Not be specific. It could be any x value. Let's see what happens then. Now, yes, this is a more complicated function, so the calculation will be a little bit longer, perhaps. But let's have a look. We have to see a couple at least. So it's x cubed, so it's c plus h cubed minus c cubed over h. All right. Now I have a bracket cubed. Now we can, maybe on the side here, c plus h cubed. Maybe you remember how to do this. Maybe you want to look it up. Maybe you want to multiply all the brackets and FOIL them out. When you FOIL them out and simplify them, you should get, actually I'm not going to do it in the line. There's no need to write it twice. You should get c cubed plus how much? 3c squared h plus 3ch squared plus h cubed, and then I have this minus c cubed still there, just squeezing in over h. And now you see that the two c cubes cancel. And in what's left, I can factor out an h, 3c squared plus 3ch plus h squared left in the bracket. Yeah, more complicated function, more algebra. It's going to happen. Then I can cancel out the h's. And what I have left is, remember, h is my variable. The c is a number. I just don't want to specify it right now. So this is a polynomial in h, which means I can plug in 0 for h, and I get 3c squared. This is now my formula. If you want to see it as a formula, you can, but it's actually a function. This now tells me original function. If the original function is my basic cube function, then the derivative, which is a function because it depends on which x value I want, whether I call it c, whether I call it x, doesn't change the fact how it's calculated. There's another pair, original and derivative. But I have to do the limit definition. Fair enough. That's a lot of work. Another one. Next one up is if my function is the x to the 4 function. You're going to have to set this up. It's going to be longer and longer because of this bracket to the 4 every time, right? More higher power here and more work is involved. I'm going to save you the trouble. If you go through the same motion, limit definition, you're going to get the derivative as 4x cubed if you've done everything correctly. So now let's have a look here. Let's have a look. We have original function. We have a couple of examples now, so we can make a list here. And we have the derivative. Original function, f of x, x squared. Derivative is 2x. Original function, x cubed. Derivative, 3x squared. Original function, take my word for it, do it if you want to, absolutely. Go through the motions. The limit definition just gets longer and longer and more tedious. But I have to do it to convince myself. I have done it. So feel free to do it as well. I get 4x cubed. Let's do one more. Now it gets very tedious. But if you have the time, convince yourself by way of the limit definition. I'm not making these up. Limit definition gives me the answer. X to the 5 times x to the 4. Is there a pattern that I can see that if I have x to the power of n, how the derivative is linked to this function type? Of course, it's very specific. It's a single power of x. Now, whether you see the pattern or not, I think everyone would recognize there is a pattern here. Definitely. It's not really hidden. The coefficient keeps increasing, so it's reasonable that the coefficient should be an n. It's the same as the power of x, right? And the new power of x is 1 less. And there we have it. There we have it. Now, we're not saying as much as you think we're saying, but we're saying something, and it's a good step in the right direction. If I have a very basic function, a single x to the power of some positive integer, then I've now gone up a few levels here. Then I can find the derivative without touching that limit definition, and that's ultimately my goal. My goal is to be more efficient, and that limit definition is the opposite of efficiency. It is time-consuming and tedious and something I honestly never want to do. I have to do it once or a few times, but after a while I'm done with that thing. Don't avoid it completely, but do it enough to realize that you don't want to do it anymore. Which means I need to find these links between the function and its derivative. And now I've seen that if I have a function that looks like x to the power of some integer, I have a formula, if you will, that links the function to how its derivative looks. We'll call that the power rule. Now, I don't like the word rule because it feels made up. I'm making up the rules. You have to live by them. That's not the case. It's more a property. It should be called the power property, but it's not. It's called the power rule, and everyone uses the word rule. Power rule. But understand, it's not made up. It comes out of the limit definition where we do it over and over and over, and we see a pattern, and that is how it behaves. Now, of course, we're slowly building up our functions, right? Right now, we can't do all the functions, even the basic functions that we have, we can't do them all at once. So we're looking at our polynomials, and we've done enough to see the power rule is what the link is behind these kinds of functions. Of course, we have other basic functions. Oops, let's zoom in one more. We have other basic functions, and there are 2 of them. It doesn't matter which one you do next. Because of the questions in the chat, we'll do 1 over x. That was another function, and that wasn't a bad function. It was a nice function, with the exception of its vertical asymptote. It was well defined everywhere else. It has tangent lines that you may want to know about. So the question of slopes of tangent lines, the derivative question, it's a very appropriate question. It's a basic graph. We should be able to answer that question. Okay. Now I'm looking at the basic one. I'm not looking at transformations on this. That could even simple transformations could make the derivative question too hard for me right now. So if I want to know at x equal to c, what is happening? Well, that's the derivative at c. There is no way. It's a new function as far as I'm concerned right now. I have to go through the limit definition. As much as I don't want to, there's really no choice. There's really no choice here. And I have a general as well because I only want to do this once. No, I don't want to do this again for this kind of function. New function, yes, I have to do the limit definition, but at least I want to do it only once. So now I want to see how this function simplifies. So I have 1 over x. So this is 1 over c plus h minus 1 over c, all over h. I'm still dividing by 0, so I can't plug in the limit value here that I'm interested in. So I have to keep simplifying until I make some progress, which means I have to put the top 2 fractions together over a common denominator, which is just their product. Then it will be c minus c plus h. And of course, these are all prerequisites. You should be super comfortable with simplifying algebraic expressions. Then this is h over 1. When I divide by a fraction, I multiply by the reciprocal. I'll leave this to be one simplification at a time. So it's h times c plus h. See, it's such a simple function. It's one of my basic functions. And this limit definition procedure is just annoying. Imagine for even slightly more difficult functions. This is not something I want to do very often. C minus C, and then I have a negative h. And I still have an h at the bottom and a c, c plus h. So the h's cancel, which gets rid of my problem, dividing by 0. But let's just see it anyway. Now, it's nice to sit back and watch me do it and see, oh yeah, let him do it. I'm not going to do this limit definition. Everything I do, that's something that you have to be able to do. Okay? You have to be able to do this limit definition, at least in one question. When h is 0, this is a rational function in h. H is my variable. I can plug in 0. I get negative 1 over c squared, because c plus 0 is another c. So, it's not that bad. You do it a few times, it's okay. So if my function is 1 over x, then my derivative is negative 1 over x squared. Is there a pattern here? Does the power rule apply? It does. This function is x to the negative 1. If I rewrite this derivative, derivative. If I rewrite this derivative, I get negative x to the negative 2. So if I take this version of the function, I move the negative 1 to the front. The new power of x is 1 less. I do get that. So the power rule still works. So really, even though the basic functions were fundamentally different from polynomials to rational functions, potentially, the power rule handles them all in their basic simple form. So now I can go back and update this. Power rule works for n being any integer, positive or negative. Of course, not 0, right? That would make no sense. I wouldn't have a function then of the same type. So it could be positive integers. It could be negative integers. It always works. If, for example, I have the function as, and we'll stop in a second, x to the, let's do it like this, 1 over x to the 5. Well, I can rewrite that as x to the negative 5. And then the power rule simply says, put the negative 5 in front, the new power of x is 1 less. I can simplify that if I want to, I might want to, or I might not want to. The power rule allows me to use the link that I've established outside of having to do the limit definition. I can sidestep all that tedious work that the limit definition gives me. I can sidestep it and find the derivative immediately. Now, of course, I have to explore this further. These are still very basic functions in their appearance, in their structure. I have to take my time. So we have to see if the power rule can be extended to more functions. And once we've extended that as far as we could, we have to see, okay, well, what else is there? When does the power rule not work? What do I do in those cases? And so on, so on. But we'll find that the power rule and some other basic properties can get us much further than you think. But it takes time to explore that. It takes time to find all these properties. But once I have it, applying them will become much more straightforward.